So we have learned about the Coulomb's law, which describes the force with which electrical charges interact with each other. So let's say we have some electric charge. Let's say we have charge of 10 microcoulombs. And then we bring another charge and place it into the point A here. And we bring charge, let's say, of 10 microcoulombs. And we measure force. But then we, in the same point of space, we remove that charge and we bring another one, let's say 20 microcoulombs. Will be force the same? We first we keep this charge stationary. We bring one charge 10 microcoulombs first at the point A and measure what the force acting on this charge. Then we take this charge away and bring another charge, 20 microcoulombs, and place it in the same point. Will be the force the same? No, will be different. So force does not describe the electric field created by this charge.
What's the title? Like electric field?
Electric field, and energy in electric field. So, then we need another characteristic, which does not depend on which charge we bring. And that characteristic is called electric field, sometimes strength of electric field, use letter E for that, and that's equal force divided by charge. In this way, this will not depend on what we bring. If we substitute force from the Coulomb's law, we get E equal K Q on R squared on charge. So we have, it depends only on the charge which creates an electric field. So electric field or strength of electric field, it does not depend on what we bring. So it describes the actual electric field. And the unit will be Newton per Coulomb. It tells us, what it tells us, the electric field. What it tells us. When we will have E equals F, for what charge? When the charge that we bring equals what?
1 coulomb.
So this tells us force which will act on the unit charge, on 1 coulomb of charge that we bring in that point. So if you know electric field, we can find force, just rearranging the formula, F equal E times Q. And let's consider the different cases of the electric field. For example, we have a single charge. The lines, and we draw lines of electric field. What is the sense of those lines? Those lines, they show lines of electric field. They tell us direction of the force acting on the positive charge if we will bring it into this point. So because this field created by positive charge, if we bring positive charge here, it will be repelled, so that will be the direction of the force. So direction of the field tells us force on the positive charge. But it tells us one more thing. Here, as you can see, lines are closed. That tells us that the field is strong. Here, the lines are more spread out. So electric field is weaker. So how close, if lines are closer, that represented field is stronger for any field. If lines are further away, field is bigger. If you will have negative charge, what will be the difference in electric field? Yes? Yeah.
The force attracting.
Yeah. It will be same shape, but force will be attracted. So the change of the direction will change. What if we will have two charges, one positive, one negative? That called dipole. This arrangement, if we have two charges, one positive, one negative, it's called dipole. And that's what we have in many chemical substances. We have effectively dipole. We have positive, negative, and the field will be between them, it will be strongest in between them, and less strong away, and direction will be always from positive to negative. That's how the shape of the, when we have electric field of the dipole, one positive, one negative charge. And if we have two, let's say, negative charges, what will happen? Same, let's say, same charges. What happens with the electrical field in the middle? They're both negative, so they create electric fields in the opposite direction. In the middle, it will cancel out. There will be no electric field in the middle. An overall electric field will look something like this. With the direction this way. With electric field, we add up, if we have two electric field overlapping, to find the overall electric field, we just need to add them, like vectors. So here in the middle, they will cancel each other. Make sense?
Why is it going inwards?
Because it's negative charge. And these lines represent direction of the force on positive charge. Positive charge will be attracted to negative. So, as you can see, when we have charges, lines of electric field, they start on positive charge and they end up on negative. When you will have to draw electric field, and there might be even on the exam questions, draw the electric field, make sure that your lines never touch or cross each other. You immediately lost mark. Why that cannot be the case that draw two lines of electric field like this? Why it will be conceptually wrong? Yes?
Because they wouldn't be able to touch each other, they would repel away.
No, lines themselves, they doesn't. What lines telling us? Direction of the force on the positive charge. So if we place here, with which direction force is acting? Don't know either there or there. It's not like we're adding them. If you draw lines and you draw that they cross or touch each other, you lose mark. Same will be with magnetic field when we will be drawing them. So if, let's say, and it's better to draw it with a pencil so you can fix it, but let's say on the exam you draw in pen and it was not much space and you are not a good artist and you draw that they touch each other, write down to your picture that lines not supposed to touch. It's only because of my bad artistic skills they touch it. You will get full mark. But if you draw and they touch and it did not explain that it just accidentally, you just cannot draw, otherwise you don't have drawing skills, then you will lose mark. That's immediately minus mark.
Have you marked an exam where someone's written at the bottom mark they're not supposed to touch?
Yes, yes. I actually seen in fact in reality I've seen that. Yeah. Yeah, and of course it's full mark, no question. And all those fields are non-uniform. Now, two terms that we need to distinguish talking about the fields. Field uniform and static. Uniform and static. What uniform means? What do you think? What uniform means in same everywhere. At every point it's same. Is any of those fields uniform?
No.
No. They stronger here, weaker there. Stronger here, weaker there. They're non-uniform. Uniform is the same in every point of space. Uniform, same in space. Static, not changing over time.
Would you say same charge in every point in space?
Sorry?
Would you say same charge at every point in space?
No, same field.
Same.
Uniform is the same field in every point of space. Static means it does not change over the time. Uniform does not change in space, static does not change over the time. How we can make uniform electric field? We can make uniform electric field in the next way. If you will have two parallel plates, two parallel metal plates, and let's say this will be plus, this minus. In the space between them, this charge with a positive charge, this with a negative, in between two parallel plates, understand that it's not line, it's like these plates. When I'm saying plates, it's like rectangles, not just lines. And the field between them will be uniform. So you draw the lines at least approximately same distance. Now, if they are finite, so they have some dimension, at the sides, that here it will start becoming non-uniform. But in between the plates, electric field will be uniform. It's same in every point of space. And when we will be looking, solving equations when electric charge moves in the electric field, that's where we will be considering motion in the uniform electric field. Yes?
How come it is uniform in the plates?
Huh?
How come it is uniform in the plates?
How it is uniform?
How come it is? Like what makes it uniform then?
Because when we add the electric field created by every point, and we add all those fields, that will be every like point charge, create electric field like this. They will be in this direction, they will be added up, in those directions will be cancelling each other out, and the result will be like this. Yes?
Did you say the curved direction lines on the outside are non?
At the edges, where it's finishing, those plates are finishing, it in fact will be curved.
So why are they non-uniform? The ones on the end.
At the end, because there is no other charge here, charges here, to add and make this. But in all equations where we will be considering motion of the charge in electric field, we don't worry about this. we consider that it's uniform, that it's just uniform.
So charge and electric field.
Now we have, and we will look into energy. So if we have a charge, we place, let's say we place electron here. What will happen with this electron? There will be force acting if you place it stationary electron. In which direction force will be acting on it?
Up.
Up. Because negative will be attracted to the positive. Negative will be attracted to the positive. So, what type of energy it will have if you just placed it there and it's stationary?
Gravitational.
Not gravitational,
Magnetic potential.
but
Electric.
electric potential energy. Because now this pen has gravitational potential energy. Why it has energy? Because if I will release it, it can do some work. Same thing with electron. If you put it there and release, it will speed up and hit the plate. So it has electric potential energy. Let's find what the formula will be for electric potential energy. And to do that, let's recall from the last year, or unit 1, 2, definition, who remember what is voltage? Definition, what is voltage? Yes?
I on
Huh?
current on charge.
1 joule of coal.
It is energy, and for energy I will be using now letter U. Why not E? Why will not be using letter E?
Because you're trying to find.
Because we already have E for electric field. We don't want to have 2E for different quantities. So U, energy over charge. Well done in remembering that. So voltage, and remember we always were talking voltage between 2 points. Voltage or potential difference. You cannot have voltage at a point. It's always between 2 points. It's amount of energy or amount of work that needs to be done to move charge from one point to another. So, energy from here, U equals UV. That is the formula for energy of the electrical potential energy. Charge times voltage. Charge times voltage. Charge times voltage.
Is the unit still in joules?
Yeah, energy in joules. Energy still in joules because 1 volt equals 1 joule per 1 coulomb. Now, let's recall what the formula for mechanical work.
Change of energy.
Yes.
Fs, force times displacement. Force times displacement. Let's say, consider how much work done. Let's say distance between the plates is d. Let's use letter d to denote distance between the plates. And let's replace charge q here. Charge q here at one plate. Then, how much work needed to be done to move it from here to there? Let's say it's positive charge, so we doing work. What the force equal? What the force on the charge in the, yes, now what the force acting on the charge? EQ, electric field times charge. So we have work equal E, Q, and the distance we move it, what distance we will move it? D. E, Q, D. So we will do work E, Q, D. And that's so much we will give potential energy. If we move positive charge, we we move. Positive charge by itself will not move there. Just positive repel. We need to push it there against electric field, so we do both. And when we move it there, it will put that much energy. So formula for electric potential energy is EQD. Yes?
Do you have to do like U and then like potential energy underneath, or?
You can write EPE, electric potential energy.
Like all caps or UEPE?
If you write U, you can write like here EPE, something like that, electric potential energy. If we compare these two formulas, what we can see as a relation between the voltage across the plates and electric field.
ED.
V equals ED. And that's energy in electric field. And let's consider if we, let's say we throw electron from the side with a speed, let's say with a speed v. How this electron will be moving? Electron, and let's forget about the gravity, because gravity is so much weaker than the electric field. There will be equations where you will be told that you need to consider, and we will be in some questions consider gravity, but let's consider only electric field. And if we like fire electron horizontally with the speed v, how it will move? What kind of motion it will be? Upwards, but how? What kind of motion?
Sine graph.
Chunky.
It will be as a projectile motion.
Oh,
It will be because either any force will be acting horizontally on the electron. No. There will be force acting only vertically. It will become pure projectile motion question. That become pure projectile motion question. Where we have angle in this example equal to 0 and the force equal EQ, and we consider that as a projectile motion question.
But wouldn't it like go up and like?
It will go up, not down. It will go like this.
So we should take this.
But does it stop? Because there's still no force. Is it friction?
Huh?
Will there be like friction that stops it from going horizontal? Or will it keep going?
Horizontally, no, there is no force. It just has
But
initial
when it
velocity.
touches.
When it gets to the plate, it's gone. It's gone because negative
Yeah.
electron will get like into the metal plate and will be then inside.
Mr. Day,
Yes.
do you just replace in the two equations for projectiles, you just replace G with E, or the electric field?
Now, what will be acceleration of the electron up? In this case, up.
But the electric
Acceleration equal force over mass. So equal force is EQ over mass. So we need G will be replaced with A, E whatever electric strength of electric field is, Q is charge of electron, which is 1.6 times 10 negative 19 coulomb, and mass of electron is 9.1 times 10 in the negative 31 kilogram. You don't need to remember any of those numbers. They're all in the formula sheet. And so let's calculate what will be acceleration of the electron if we have that strength of electric field. Electric field is the electric field is 0.91 Newton per coulomb. What will be the acceleration of the electron? I made numbers very convenient, so you don't have to use a calculator. Come on, we have E equals 0.91, divide 9.1. 9 and 1 cancels out, so what will left?
1.6 times 10 to the 11.
1.6 times 10 into the,
I may have done that wrong.
so 1.6 times 10 into, and we have 0. That's negative 31, and when we divide we get another negative, so we divide by that, it will be 10 and the 32, yeah, 11.
Oh.
10 power 11.
Hold on.
Coincidence.
So it will be a huge acceleration. It will be a huge
Is that still
acceleration.
meters per second? Square?
Yes, meters per second. Okay, and one more example. Now let's consider if there is a gravity. If there is a gravity. Let's say what should be the strength of gravitational field? What should be the strength of strength of electric field to have electron being stationary here in the electric field? What should be the strength of electric field for electron to be stationary? Yes.
I just have a question for that.
Yes.
What's the units for acceleration?
Meters per second squared.
It's EQ on M.
M.
Still accelerating.
It's still meters per second squared. It came from force over mass. Yes.
Is it 9.8? So you asked about the.
Strength of electric field. You will have, if it be stationary, what does it tell us about the forces? About the net force?
0.
0. Which forces we have? Mg down and F electrical up.
What's that?
So we have F electrical equal Mg. We have QE equal Mg, right? For them to be stationary. Electrical force equal force of gravity. So we have Q 1.6 times 10 negative 19 times E equal 9.1 times 10 negative 31 times 9.8. E will be equal, that will be can you please check with the calculator how much I 5.6. Okay, 5.6 times 10 in the negative 11. So you see that so weak electric field will oppose gravitational field and keep electron.
Junior right.
Unit is newtons per coulomb. And that's the way how the charge of electron was actually found. We will talk, there was famous Millikan experiment, which we'll discuss later on. Yes,
What if the charges of the plates were flipped so the positive was like going down?
if positive will be down, then we will have both gravity and electric field acting down, and what will happen with the electron?
So it can't remain stationary like that.
Of course, if only all forces will be
Yeah.
down, it cannot. It has to be that electric has to be up to oppose gravity. Okay, like, subscribe, and donate to help fight with Putin and support Ukraine and Israel.